Hello, my dear Betcho, and welcome back. Exams are so close, I can feel the tension building up. But hey, don't you worry at all. Today, we are going to just breeze through electromagnetic waves. It's a small, sweet chapter, and trust me, full marks are guaranteed here. So just relax, and let's get you fully prepared. Just look around you for a second. You're probably watching this on your phone, right? You change the TV channel with a remote, you heat up food in the microwave, and all of this happens without a single wire. How? Is it some kind of magic? Well, no, it's pure physics. And the hero behind all this magic is the electromagnetic wave. So come on, let's find out what this is all about. So, our story starts with this absolute genius, a scientist named James Clerk Maxwell. Now, he was studying the big laws of electricity and magnetism, the ones everyone thought were perfect. But then, he found a problem. A big one. It was like finding a missing piece in a giant jigsaw puzzle that everyone else had missed. And the problem was with Ampere's law. Now, this law is a big deal, okay? It basically connects an electric current to the magnetic field around it. Simple enough. But Maxwell found a specific situation where this law just failed. When he tried to apply it to a capacitor that was charging, the whole thing just fell apart. What a mystery, right? Okay, look at this picture. This shows the exact problem. See, the current flows nicely through the wire, but then it reaches the capacitor, and poof, it stops. There's a gap between the plates, right? The electrons can't jump across. So according to the old law, if there's no current in the gap, there should be no magnetic field there either. But when they actually checked, they found a magnetic field in the gap. How is that possible? A complete contradiction. So what did a genius like Maxwell do? He came up with an idea that changed physics forever. He said, Okay, you're right. No actual electrons are flowing in the gap. But look at what is happening. As the capacitor charges, the electric field in the gap is changing. And he proposed that this changing electric field itself behaves like a current. He gave it a cool name, displacement current. What a mind, huh? And this, my dear students, is the most beautiful part. It's like a perfect partnership. We already knew from Faraday's law that a changing magnetic field gives birth to an electric field. And now Maxwell showed us that the reverse is also true. A changing electric field gives birth to a magnetic field. They create each other, back and forth, back and forth. And this dance, this is exactly how an electromagnetic wave is born. Okay, so we know how they are born from this amazing dance. But how do these waves actually travel through space? How do they get from, say, the TV tower to your home? Let's find out. Think of it like a non-stop chain reaction. It all starts with one tiny charged particle that's accelerating, basically just wiggling around. This wiggle creates a changing electric field. That changing electric field then creates a changing magnetic field. And that magnetic field creates a new electric field a little further away, and so on and so on. It's just like a viral Instagram reel, One person shares it, then the next, and it just spreads across space forever. Now, this diagram is super important. Look closely. The electric field, the E field, is going up and down. The magnetic field, the B field, is going in and out, side to side. And the wave itself is moving forward. See? All three, the E field, the B field, and the direction of travel, are at 90 degrees to each other. They're all mutually perpendicular. This is what makes it a transverse wave. Please remember this property. Okay, now write this one down. This is the boss equation of this chapter. It's super simple, but super powerful. The peak value of the electric field, which we call E naught, divided by the peak value of the magnetic field, B naught, is always equal to C. And what is C? The speed of light. You're going to need this for solving numericals, for sure. All right, seatbelts on. We're going on a super quick tour of the entire electromagnetic family. We'll meet everyone from the big, lazy radio waves to the super energetic gamma rays. Ready? Let's go. First up, we have the long wavelength guys, radio waves and microwaves. Think about it. Everything from your favorite FM radio channel to the call you make on your mobile, even your Wi-Fi. It's all thanks to them. And of course, who can forget the microwave oven for that instant popcorn? Moving on, we have infrared. Now, you can't see this one, but I bet you use it every single day. Your TV remote? That's infrared. It's also basically heat. You know when you feel the warmth from a bonfire on your face? That's infrared radiation you're feeling. That's why we also call them heat waves. And now for the star of the show, visible light. Can you believe it? Out of this massive, huge family of waves, this tiny, tiny little sliver is the only part we can actually see with our own eyes. Every single color, the whole Vibgyor rainbow, it's all packed into this one little section. Amazing, isn't it? Next up, a bit more powerful, we have ultraviolet, or UV rays. The sun is the main source. It sends tons of UV our way. But luckily for us, we have a superhero protecting our planet, the ozone layer. We also use UV rays in a good way, like inside water purifiers to kill all the germs. And finally, we have the heavyweights, the most powerful of them all, X-rays and gamma rays. These guys are so full of energy. X-rays can go right through your skin, which is why doctors use them to see your bones. And gamma rays, they are even more powerful. We use them in medicine to fight and destroy cancer cells. So you see, they are lifesavers. Okay, everyone, phones out. This slide is your golden ticket for revision. Everything we just talked about, all the waves, all their main uses, it's all here in one simple table. Seriously, take a screenshot right now. This is perfect for those one-mark questions and for that last-minute revision before you walk into the exam hall. All right, enough theory, Sherry. Let's get our hands dirty and crack an actual exam question. And I'm telling you, the questions from this chapter are practically free marks. They are some of the easiest you will see in your whole physics paper. Don't believe me? Let me show you. So here's the question, a classic one, straight from your textbook. They've given us this big, long equation for the magnetic field, and they want us to find the wavelength, the frequency, and the equation for the electric field. I know, it looks a bit scary, but trust me, it's really, really simple. Okay, for part A, the only trick is to compare. That's it. Compare this given equation to the standard wave equation. See the number that's next to the x? That's your k. And the number next to the t? That's your omega. Once you've got k and omega, the rest is cake. Wavelength is just 2 pi by k. Frequency is just omega by 2 pi. Put the numbers in, do the simple math, and boom, answer done. See, I told you it was easy. Now for part B. Remember our boss equation? Time to use it. We need to find E naught. Simple. It's just B naught times C. Now, what is B naught? It's that first number in the equation, the 2 into 10 to the minus 7. Just multiply that by the speed of light and you get 60. The rest of the equation, that whole sign part, it stays exactly the same. Don't change a thing. Finally, if B is along the y-axis and the wave travels along x, then E has to be along the z-axis. And you are done. Full marks, just like that. Okay, final lab. Let's do a super fast 1-minute revision to make sure all these important points are permanently stored in your brain. Are you ready? Let's go. Number 1, a changing electric field creates a magnetic field. That's displacement current. Number 2, where do EM waves come from? An accelerating charge. Got it. Number 3, they are transverse. E, B, and direction, all perpendicular. Number 4, in a vacuum, all of them, from radio to gamma, travel at the same speed, the speed of light. And number 5, the boss equation. E naught by B naught equals C. That's it. You know the whole chapter now. And that's it, my dear Bachcho. The entire chapter done and dusted. You see how easy it was? You have prepared so well, and I know you're gonna do great. So please don't take any tension. Just be confident. You've got this. All the very best for your exams. I'll see you in the next one.